Hey everyone, and welcome back to PrepFusion. So we'll start the part 2 of this lecture 0, that is Introduction to Power Electronics. So in the previous lecture we learned what is power electronics, why is it needed, and in those power electronics we need particular devices known as switches to help us accomplish that whatever we want, right? And to understand switches we have to understand switching characteristics and also switching losses, what losses they give out, and also what type of characteristics they have. So after that we'll study about construction of switches. For now we're just getting an overview circuit analysis of switches. So I told you how to compute losses, how to compute the switching losses, and what are the timing characteristics. So in this lecture we'll mainly solve the assignment question which I gave you in the previous lecture. So let's start with this question. So this question is telling us that a diode is having a IV characteristics as shown below. If it is used in a half wave rectifier circuit with resistive load and carrying a peak current of 100 amps, determine the average conduction loss in the diode. So first of all, IV characteristics of a diode is given. Now can we identify this? If you have studied analog electronics, you will be able to easily identify this is the third model of a diode, okay, which is the piecewise linear model. So in this model, right, what happens is that the slope of this gives us the on resistance of the diode, and the x intercept gives us the V gamma, that is the forward voltage drop when the diode is turned on. So if you know, very good. If you don't know, like now you know, right? And anyways, I told you analog electronics you must study before coming to this, at least the 3 chapters, that is first chapter, then like the second chapter, that is the MOSFET. I hope you have studied from us only, so you know all these things. So the slope of this gives us the on resistance. What is the slope? Slope is basically di upon dt, the inverse of the slope. So this will be 1 by r on, right? 1 by r on, which is equals to dv is 1 and dy is 200. So 200 by 1, so r on will be equals to 1 by 200, or it will be equals to 0.5 kilo ohms. Anyway you want to say, okay, well, not sorry, r1 equals to 1 by 2, not 0.5 kilos. r1 equals to 1 by 200, right? Very small number. Then V gamma is this is the V gamma. So basically I can replace my diode like this. Diode can be replaced with the R on and a forward voltage drop. Now this is V gamma. V gamma is 1 volt and R on is 1 by 200 ohms. The next important portion is that about half wave rectifier. Now if you have studied analog electronics, there I have taught a bit about rectifiers and filters, okay, and I have taught what is a half wave rectifier. All these things I have taught, and anyways in college also you have a basic idea what is half wave rectifier. So we will study this in a more in-depth manner in the second chapter, but for now you just know what is a half wave rectifier. It just conducts for the half cycle of a sinusoid wave, okay. It basically gives only the positive output, and negative output it rejects. So if it is carrying if the half wave rectifier circuit with average load of with resistive load and carrying a peak current of 100 amperes. So how does a half wave rectifier circuit look like? A half wave rectifier circuit looks like something this, and it has a resistive load R. This is my supply, okay. This is the most basic half wave rectifier with a single diode. This I have taught in my analog electronics, rectifiers and filters. So this is a V input, and it has told that the peak current through this resistor, right, will be 100 amps. So if the peak current is 100 amperes, that means when will this peak current happen? When this diode is on, okay, when this diode is on and it is flowing the current, like current is flowing. So if current is flowing, only when the input voltage is maximum, then only peak current will happen. Now what I will assume here, the thing that we need to assume is that assume when peak current happens, we neglect the drop across diode. So like the peak current will be very high and we will neglect the drop across diode. So I should also mention in brackets here that drop across diode neglected, because peak current will be anyway so high that we can neglect for that particular reason only, because peak current is very high. Okay, if one number is 100 and another number is 0.1, so obviously 100 is very large than 0.1. So even if I add 100 and 0.1, it will be 100.01, and that won't make much of a difference. That's why, so we can neglect it. So when peak current happens, that means I have been given the IM is 100 amperes. Okay, and for a half wave rectifier, right, if I know the IM, I can find everything. Okay, because if you remember, like the formulas, you can do the integration, but like you can go and study from me in during the half wave rectifier, or if you don't want to study, don't worry, just understand that this is the formula. We will derive this all in the second chapter, don't worry. Okay, so I average I can write as IM by pi. Okay, so I average is IM by pi, and I RMS I can write as IM by 2. Okay, these are the formulas. This I have derived in my analog electronics course in the rectifiers and filter portion, and also I will derive here as well in the second chapter. Don't worry. Just for now, believe in me that this will be the results. So what I can say is I know IM, right? IM is given, so I can compute I average and I RMS. Now, why do I need I average and I RMS? If you remember, I just derived to you that the loss across a pulse, piecewise linear model of a diode, right? It will be something like this. It will be V on into I average plus I RMS square into R on. So I need I RMS and I average, these two data points. So that's why I need to compute I average and I RMS. And this is the piecewise linear model. So my I average will be 100 upon pi. So if I just compute 100 upon pi, if I can find the phone, yeah, 100 upon pi is, it will be somewhat 31.83, something like that. Let me just quickly do it. 100 upon pi, yeah, 31.83. 31.83 amperes, and I RMS will be 100 by 2 is 50 amperes, right? And what will be my loss? What will be my conduction loss? It will be V on into I average. I have derived how this comes up. I will not derive it again, and it will be I RMS whole square into R on. Okay, so it will be I average whole square into R on. So this will be equals to V on into I average. V on is the forward voltage drop, right? Forward voltage drop across the diode, which is 1 volts. So it will be 1 times I average, which is 31.83 plus I RMS whole square. RMS is 50 whole square into R on. R on is how much? 1 by 200, right? So divided by 200, which will be 12.5. So overall, what will be my power loss? If I add this 2 up, this will be 31.83. So this will be equals to 44.33 watts. Okay, this will be my conduction loss. This will be my conduction loss. So this will be the answer to this question. Pretty straightforward, but just you have to identify what is half wave rectifier and all those formulas. So with those, this becomes very difficult question, and to be honest, this should be in the second chapter, but obviously as we are studying about switches now, so I have to do it now only with the flow. Just don't worry, this formulas, right? This formulas we will derive in the second chapter, and if you want to learn now, so I hope you have studied electronics. If you haven't already, like, it will be in the prerequisites that you have to go through that rectifiers and filters thing. Okay, it will be in the prerequisites. So this is about the third question. So let's go to the more assignment problems. So next we were discussing about switching power losses, and I solved one question, and this question I gave you as homework. Let's solve this fifth question. So in this again, you will see me, I will try to use minimal formulas. Okay, I will try to use minimal formulas. I will try to solve with basics. Even though I have derived formulas for this, I will try to use minimal of them. So here, this is the first question where the voltage Vs and Is through a semiconductor switch during turn on transition are shown. The energy dissipated during the turn on transition in millijoules. Take care of the units as well. So can we identify this as a turn on, even if you wouldn't have mentioned about turn on? Can we identify is this a turn on or turn off? So yes, right? So here Vs is constant and Vs is reducing and Is is increasing. So as Is is increasing, switch current is increasing, obviously it will be a turn on. Now next, what is the thing? They have asked us to find the energy dissipated. For finding the energy dissipated, it will be basically integration of power over T on time. Integration of power over T on time. Okay, so obviously for that we need power, right? So either you can write here equations and all those things. I will just do it with graph. You will see I will just do it with graph and I will not use any equations. So it will be the area under the power graph from 0 to T on time, right? If I assume this as my 0 time, okay, from this instant I am assuming T equals to 0. So after this everything is changing, right? So how will my power graph look like? So my power graph will look something like this, that anyways this is 0 before this, so anyways the answer will be like the product will be 0. So if I start from here, okay, and then what is happening, this current is increasing linear fashion, but this voltage is constant in this T1 time zone, right? So it will get scaled only, the shape will remain same, just as I have solved previously as well. So this will get scaled only. This will be the graph of P of T. Okay, next what is happening? So what is the value up here at the peak? At the peak, this value is what? This value is 100, this is 50. So overall this is 150 of height, and this is how much? This is 600, right? So 150 times 600, it will be 150 times 600, so it will be almost 90 kilowatt, right? 90 kilowatts. I will just do it 150 times 600, yeah, 90 kilowatts. So this will be 90 kilowatts. Let's just do this. 90 kilowatts. Okay, so this will be 90 kilowatts. Now what is happening at this T1 instant? This is the T1 instant. This is a T1 instant. T1 instant. So at this T1 instant, right, just after 1 microsecond, the current is suddenly reducing to 100 amps. So it reduced by 50 amps. So it is currently 100 amps and voltage is now linearly decreasing. It is still constant here. So this is constant and this is linearly decreasing. So overall the shape will be linearly decreasing, and it will be just scaled with by 100, right? It will be just scaled by 100. So from 600 so into 100, it will be going to 0. So it is 60 kilowatts. So suddenly what will happen is that this will reduce to 60 kilowatts because the current reduced by 50 amperes. So this is 60 kilowatts, and then again it is linearly decreasing for T2 time. Okay, so T1 equals to 1 microsecond and T2 equals to 1 microsecond again. So this like widths are same only, and this is basically the graph. So I need to find the area. So I can divide it into two sections. One is this half right angle triangle and one is this half right angle triangle. So I can find the area of these two individual things. So basically this will be like they have asked us in milli, right? Millijoules. So what do I notice is kilo times micro will give me milli, right? So kilo watt times microseconds will give me milli. So I don't have to do any conversions, just write the expressions as it is. So basically if I compute the energy, energy is equals to half into base into height. So half into base is T1, that is 1 micro, into height. Height is how much? 90 kilowatts for this first triangle. So I will break it down into two triangles. This is first triangle and this is second triangle. So this will be half into base into height, 90, plus half into base into height, 1 into height, 60. Okay, so this will be basically 45 plus 30, that is 75 millijoules. So you see, right, the answer was so easy, but if you want to do it with equations or formulas, it would be so difficult for you. So that's why always have basics clear. So the answer for this question will be 75 millijoules. Answer for this question will be 75. Now let's move on to the next question. So in the next question, the forward characteristics of power semiconductor device is given, that is Vi equals to 1 plus I, where Vi is the voltage and I is the for Vi and I are the voltage and current across the diode. For the current waveform shown below, the average power dissipated in the diode will be. So current waveform is shown below. What will be the average power dissipated? Now this question, right, is almost similar like previous question, like this question, not this one, the second question one, this question, right? Just here the on resistance was provided for this switch device. Now what has been provided? If you observe this equation carefully, this is basically what? This is the piecewise linear model of a diode, if you observe carefully. So basically whenever Vi is equals to, it is written something like this in a linear fashion, 1 plus I. So basically this, they are talking about the piecewise linear model here, right? This one means the drop across the diode to turn on, so it is 1 volts, so it is a forward drop, so this is the 1 volts, okay. And this, right, the slope of this or the coefficient of this represents the slope of this Vi and I. So it is the on resistance. So in this case, right, on resistance is 1 ohms, which is pretty high actually, pretty high, okay. So loss will be also pretty high. So on resistance of this switch and the cutting voltage is 1 volt. So this is a linear piecewise model. So computing the power will be easy again. It will be P equals to V on into I average plus I RMS whole square into R on. Okay, so how this formula came I have already explained, or you can anyways understand, right? What you can understand is that like how this formula came. So I did this with basic in the previous lecture, you can go to that, or like you can see that this is DC, so this will be the average power. DC times average power will be this power, and this is the RMS, right? So RMS whole square will be the AC component of the power and DC will be the average power. Okay, so now let's like put the values and find out. So what is the average current in this? Average current in this is IO average. IO average is basically the area under one cycle. So I will just copy this graph, okay, and compute the IO average. So if you observe here, IO average means the area under one time period, average of the area of the under one time period. So this will be equals to area of this square or rectangle 10 into 3d by 4 plus 0 divided by overall time is t, time period is t. So this will be simply 7.5 amperes. This is the IO average. What is the IO RMS or the IRMS? I should mention, not IO, you will get confused. IRMS, right? IRMS, it is the root of the mean of the square of the area. So basically this will be, I have taught this in my network theory course, how to compute RMS and all those things. This will be 10 square into 3t by 4 divided by t, and we have to take the under root as well, or raised to the power 1 by 2, raised to the power 1 by 2. Okay, so this will be 100 divided 75 under root. So what is this exactly equals to? Let me just quickly compute this. Just hold on, where is my phone again? My phone is here. I will compute this under root 75. 75 under root is 8.66. 8.66 amperes. 8.66 amperes. Okay, so this will be the IRMS. So we have computed I average and IRMS. So I will just put those in the expression. I already know V on and R on. So V on is this, right? This is V on, which is 1 volts. So 1 times I average, which is 7.5, and R on is 1. So 1 times IRMS whole square. So it is 8.66 whole square. Anyways, I will require only this only. Okay, even if I wouldn't have computed this 75 under root, it wouldn't have mattered. So obviously you can save computation time here. So this will be 75 plus 75, which will be equals to which will be equals to 82.5 watts. So basically, right, this will be your answer. As here our IRMS was very R1 was very high, so that's why the loss also came out to be very high. Generally this much high amount losses doesn't occur. Okay, obviously this is a very high loss, and this is just a simple theoretical question. That's why in practically this much high loss won't have happened. So let's solve this seventh question. So in this seventh question, what have they told? A thyristor in an application carries a half sinusoidal current with 2 millisecond period. Okay, so thyristor is carrying half sinusoidal current, so obviously it is acting like a rectifier. So if I do it with 2 millisecond period and 10 ampere peak, so 2 millisecond period means frequency is 50 hertz. So this thing should be mind, right? So not 2, sorry, frequency is 500, because what does 2 millisecond means? 2 millisecond means, if I do 1 by t, so this will be 1000 by 2, right? Yeah, 500, not 50. 50 is for 20 milliseconds. 20 milliseconds. This will be 500 hertz or 0.5 kilohertz. Okay. So this is T. This is my current across the thyristor, which is half sinusoid. So half sinusoid will be something like this. Thyristor is basically a switch also. I've already explained in the overview, right? Thyristor, like, and different types of thyristor. I will obviously go more in depth in the next few lectures. So it has a peak current of 10 amperes. Okay, it has a peak current of 10 amperes. And the thyristor can be modeled during conduction with on resistance of 0.5 ohms. So it has a on resistance R on of 0.5 ohms. So thyristor can be modeled like a resistor basically when it is on. When it is off, it is totally off and no current is getting conducted, so there will be no losses. Determine the average conduction loss in the device. So conduction loss means when the device is in on state. So basically, what will be the average loss? So we have used the second model. So this time it will be peak conduction. Peak conduction will be basically IRMS whole square into R on. So IRMS whole square into R on. So IRMS is what? IRMS is basically this, right? And what is the RMS of half sinusoid? It is peak by 2, right? This I have used in the previous questions also, and this I will teach you in the next chapter, and this has been taught in the analog electronics, rectifiers and filter. So basically for a half sinusoid it will be peak by 2, and if I do the square of this, it will be 25 basically, and into R on, right? This will be the loss basically. So like you see, right, the switches question you will be able to solve in seconds if you know the basics. So 25 into 0.5, which is 12.5 watt. So this will be the conduction loss of the device if the device carries these type of current. Okay, so pretty simple. So now let's move on to this question. This is the best question of basically of the assignment. Like, this is the main question. So here, right, during switching operation of a semiconductor device, the voltage and current waveforms of the switch are shown here. Okay, voltage and current waveforms of the switch are shown here. For a switching frequency of 50 hertz, find the average power loss during the switching. Average power loss during the switching means this is the whole period. And what is the average power loss? Average power loss here and average power loss here as well. Okay, next, maximum switching power loss during on and off period, on and off operation. So this is talking about the average. Okay, average power, and this is talking about the instantaneous, because maximum power can only happen occur only once, right? It can't occur twice or thrice. Okay, so this is talking about the instantaneous power. Now you might say, sir, they haven't provided us this time, so how will I compute average power? Because for that, in the bottom side, I need the switching frequency as well, right? Or the time period, overall time period of the switch. So here, right, if you observe, they have given us the switching frequency. So with the switching frequency, we will be able to compute the time period. Okay, so if you remember, I've derived this formula. I will not like derive it here again, and like you can solve from basics as well. That's no issue. Okay, you derive the formula by yourself. But this was the total energy lost in the switch when these type of waveform is happening, right? The total, like when this is the during turn off and turning on. Overall energy loss was turn off plus turn on was this, right? So I should have drawn the waveform here as well, that it is turning on and off, overall switching loss. So overall this switching loss will be on and off. And just here the good thing is I've told there as well that this value needs to be same. This value needs to be same. So what I will do is what I can do to make this more generalized, right? I can write this formula in a more better manner. That okay, can I write it more better manner? No, right? Like else this will become lengthy. So what I will do, I will keep this here. Just hold on. Keep this in the bottom. I will copy this. Paste this here. Okay. This is here. This is basically like what I can do is this T on will be here only. This will be V on into I on. So during on period, what was the peak current and the peak voltage, and during off period, what was the peak current and peak voltage. So this is a generalized case, and when the peak current and peak voltage for the both the cases is same, so this won't change anymore. So if V on equals to V off and I on equals to I off, so the formula becomes somewhat like this. And in our case, right, in the last case it was same, but if it wasn't same, we have to use the generalized formula just written now. Okay, so basically what we know that total energy lost during the switching E switch is basically V into I divided by 6 into T on plus T off for these particular characteristics. If this wasn't given, obviously we had to solve with the area of the graph and all those things, right? We know all this and we have just derived it. That's why we will use our formula. So this is some value, and for computing the average power, right, average power, we just have to divide E switching by total time, and this like time period basically, and this I can write it as E switching into frequency, right? 1 by T is F. Okay, switching frequency, this is the switching frequency. So they have given me the switching frequency. Now I just compute the ESW. So what is ESW? It is VI by 6 into T on plus T off. So T on is 2 and T off is 1.5. So what is V? V is 500. I will write 50 into 2, because what will happen is that other 3 zeros, right, other 3 zeros will get cancelled with this milliseconds. So I am just doing the computations here, or like just to make everything clear, I will not do that. So 2 into 200 divided by 6 into T on plus T off, that is, this is 2 and 1.5, this is 3.5 into 10 raised to power minus 6 into 50, not 6, sorry, minus 3. So what will happen here is that this will go away, and okay, I will just compute this, and this will be in kilowatts. Actually switching loss will be in kilowatts because the current and voltages are very high. So 50 into 2 divided by 6 into 3.5 into 50. Okay, yeah, 2.916 kilowatts. So answer will be 2.916 kilowatts. Okay, so this will be the answer to your question. So you will say, sir, you use formula. I use the formula, but I derived it, right? So few times it's good to remember the formula, just like the rectifier case, half of rectifier case. Like those are basic things, and those will be required everywhere in analog electronics, in network theory, in power electronics. If it is getting used everywhere, obviously you should remember that. It will be helpful, right? Because it is getting used everywhere, so it's worth to remember that. And here also this is worth to remember that, because deriving it will waste your time. Okay, simply saying whatever you need to derive, that I will say to you. I will speak out to you that you need to derive this, and you can derive this in the examination hall. But deriving this, you can obviously do it if you have time, but this will be waste of time. This formula you can remember, and how it came, I have told you how it came. Okay, so answer to this question will be 2.906 kilowatt, not SW. This is the PSW, right? So first one is PSW. Next one is what? The maximum power. Now the maximum power happens when both of them are maximum, is it? No, right? Because both of them, I can't find any case for both of them are maximum. So how to find out the maximum switching power during on and off operation? So for this, you have to again go back to basics. When you don't know anything, you have to derive it by yourself. So this one I knew, so I didn't have to derive. I used the direct formula. But this one I didn't knew, so I cannot derive. Like I cannot just write any formulas. I have to derive from basics. So when does maximum occur of a function? Maximum occurs when its derivative is 0. So first of all, I have to write power in terms of time, and then I have to make its derivative 0. Then only I can find at which time the maxima is occurring, and at that particular time I will compute the value of power, and that will be the maximum power. So basically, now for this case, right, many students, if they have studied previously, they will say, sir, this is so easy, this will be just in this region, right, where at this t equals to t by 2, and at this region both of them will be like the power will be maximum. Great, you remember the formula. But what if they give a graph something like this? Can you tell me when will the maximum be? No, right? So just for any random graph, you won't be able to tell. Like this few students remember the result of this. That's great. But if in some day they give some random graph, you won't be able to derive it. So it's better to remember the formulas, but it's more better to know the derivations as well. How did those derivations came, so that you can derive in the examination hall when something weird happens. Okay. So in this case, right, I have to write power in terms of time axis. How will I write? It is V of t into I of t. Okay, so my time for this on period, right, my time here is it's starting from t equal to 0. And what is the V of t expression? It is reducing from 500 to 0. So delta V is what? Minus 500, and delta t is 2 milliseconds. So it will be for this voltage, right? What will be my V of t? V of t delta V is minus 500, and delta t is 2 milliseconds. So this is 2 milliseconds. Okay, I will write this like 2 into milliseconds, because I will assume that my time is also in milliseconds, so that cancels out. So, and what is the x-intercept? X-intercept will be at t equals to 2 milliseconds, my voltage should be 0. So at t equals to 2 milliseconds, it is minus 500, so it will be plus 500. And here I will mention t in milliseconds. What is the expression for I of t? So the expression for I of t is same. Expression for I of t will be, again, delta I is 200, delta t is 2 milliseconds. So it will be 200 by 2 t plus what? 0, right? There is no x intercept here. So so this is the thing. So I will just put these values here, and then I will take the derivative, and at that time the maxima will occur. So my P of t, just write in different color, my P of t will be V of t into I of t. So V of t is basically minus 250 t plus 500 into I of t, which is 100 t. So this will become, my P of t will become something like this. If I take the derivative, right, so P dash of t equals to 0 at t equals to Tm, my power will be maxima, right? So if I take the derivative of P dash of t, what will be it? It will be minus 250 t plus 500 into 100 plus, this is minus 250 into 100 t, right? So if I equate this to 0, this will be minus 250 t plus 500 this is also minus, right? Yeah, this is also minus 250, t equals to 0. So at t equals to 1 millisecond, t equals to 1 milliseconds, so tm is equals to 1 millisecond, right? This is tm, where I'm equating it with 0. So tm equals to 1 milliseconds. What I'm getting the maxima power. I'm getting the maxima power. So if I put t equals to 1 milliseconds in this expression, what will I get? This will be 250 and this will also be 100. So total I will get 250 kilowatts. So p of t at t equals to 1 milliseconds is equals to 25 kilowatts, and this will be the maxima power. As I am getting only one value, and you can compute, like you can make sure with the double derivative that it is the maxima only, not the minimum. Obviously it will be maxima. Okay, you can check for yourself. So this will be the maximum value. So the few people remember the results. It is basically VI divided by 4. So VI is 10 kilowatts divided by 4 is 2.5 kilowatts. Sorry, not 10. In this case it is 100 kilowatts. 100 kilowatts divided by am I correct? 3 zeros are here, and yeah, 50 into 2, that is 100. Yeah, 100 kilowatts divided by 4, that is 25 kilowatts. So 25 kilowatts is the answer. Few students remember. For this graph, yeah, it is correct. But if the graph is someday different, you won't be able to do it. You have to solve by yourself only. So what I will do is I will give you the homework for the minima one. Like in this case, the hint is it is same only, not minima. Sorry. Here during the turn off process, what will the maximum switching loss? It will be same only, because this and this graph are same. But what if the graphs were different? Then things would have been different. But what I want to do, you just write the expressions for voltage and current and prove for yourself that it is correct. If you prove right, then only you will understand that you have understood the concept. You have to do things by yourself. Just watching me won't make the cut, and you won't clear the gate examination if you just keep on watching me. So I will do this. I will do this here, but I wanted to do by yourself. I won't do in front of you. Okay. So P max during the off period. This was the P max during the on period. Okay, on period. This is A and this is the off period, right? This is B. Second question only, B question, B part. Okay, this is the homework for you. This you have to do by yourself. So that's it basically about the introduction to power electronic devices and about the switching losses. So obviously we'll know more about switching losses, more know about switches in the next lecture. So from the next lecture we'll understand what are basic switches and what are different types of switches and the characteristics and construction of different switches. Until then, I will see you again. Thank you for watching PrepFusion.